Hello everyone, and thanks for watching Edupedia World Videos. In this video, we start a new quantum mechanical problem, that is the delta function potential, and this will be the first example we will see both bound state solutions as well as scattering state solutions. So first, let's look at what the delta function is. It is more commonly known as the Dirac delta function. Written as delta of x, and basically delta of x is 0 if x is not equal to 0 and is infinite if x is equal to 0. So the graph of the delta function looks something like this. It is 0 everywhere, and then it is infinite at one point, and then it goes back to 0 again. But it also has one more special property, and that is the integral from minus infinity to infinity, delta x dx is equal to 1. So there is a restriction which tells us that the total integral is 1. And this doesn't necessarily need to go from minus infinity to infinity. It can also go from minus epsilon to epsilon, because all we need is any interval containing the point x is equal to 0. If you took the interval delta x dx from 2 to 3, then it would be 0, because this interval does not include x is equal to 0, which is the point where you have the delta function. An interesting property of the delta function is, whenever you put the delta function multiplied by another function inside an integral, for example, integral of minus infinity to infinity f of x times delta of x minus a dx, this can be written as, now f of x into delta x minus a. Delta x minus a is 0 except where x is equal to a. X is equal to a is the only point where this gives a value, so we can replace f of x by f of a, because everywhere else it's 0. And f of a can come out because it's a constant, minus infinity to infinity, delta x minus a dx, and this term we know is equal to 1 because it includes the point x is equal to a, so this is equal to f of a. So this is the most important property of the delta function. In fact, the delta function is generally used under an integral. The main properties of the delta function are the things which does when it is inside an integral along with another function. Integral minus infinity to infinity f of x delta of x minus a dx is equal to f of a. The potential we'll deal with, v of x, will be a delta function well, means it will not be in the upside, it will be in the down direction. And we'll take that to be equal to minus alpha delta of x, and alpha is just a scaling constant, so that we have another variable which tells us the strength of the delta function potential. So let's start with that. We have the potential v of x is equal to minus alpha delta of x dx, which means the potential looks something like this. It is 0 everywhere except at x is equal to 0, where it is minus infinity, then it goes back to 0, right? And so we use the Schrodinger equation, which we know what it is, the time independent Schrodinger equation. Again, I'll just repeat one more time. If the potential explicitly depends on dx, if the potential explicitly depends on t, then we have to use the time dependent Schrodinger equation or the general Schrodinger equation. But if the potential explicitly does not depend on time, then we did in one of the previous videos, divided it into two parts, and we got the time independent Schrodinger equation, which was basically minus h square by 2m d2 psi by dx square plus v psi is equal to e psi. So now we can just replace v by alpha delta x, so what we'll get is minus alpha delta of x psi is equal to e psi. And this particular problem will yield both types of solutions, those with energy E less than 0, which will be bound states, and it will also give solutions for energy E greater than 0, which will be scattering states. So let's start with E less than 0, that is bound states. And we'll solve this in two separate regions. Region 1, which is x is less than 0, and region 2, where x is greater than 0. Because in both these regions, v of x is 0 everywhere. So for region 1, x is less than 0, what we get is d2 psi by dx squared is equal to minus 2me by h square psi, because this term becomes 0 for every point such that x is less than 0. And this we can write as k squared psi, where k is just a constant which we define as k is equal to root of minus 2me by h. Now this might seem peculiar to you why we have a minus inside a root sign. That because right now we are doing the bound state energies where E is less than 0. So if E is less than 0, this whole term is positive, and that's what we have written to be k squared psi. Now you know this from mathematics, when d2 psi by dx squared is equal to minus k squared psi, where k squared is a positive constant, we get sin kx plus cos kx. But when it is equal to plus k squared psi, we get the solution psi of x is equal to a e to the power minus kx plus b e to the power kx. And if k was actually, k squared was negative, then iota kx and minus iota kx, which would basically be the same as a sin kx plus b cos kx. So this is the solution for x less than 0. But we know that as x is less than 0, psi of x has to go to 0 as x goes to minus infinity. So this term will blow up if x goes to minus infinity, so a has to be 0, which means psi of x is equal to b e to the power kx for x less than 0. Right, a has to be equal to 0 because if a was non-zero, as x goes to minus infinity, this term will blow up. But we need this term to go to 0. Here, as x goes to minus infinity, e to the power minus k into infinity does indeed go to 0. Similarly, we can do the solution for psi x greater than 0, and you can do that yourself. And what we'll get is it's equal to some other constant. You have a, b, let's say you choose constants f and g, f e to the power minus kx plus g e to the power kx, where k will have the same value. Then in that case, g will become 0. And what we will be left with is f e to the power minus kx for x greater than 0. So this is basically psi. We've been able to calculate it, and if you wanted to graph the value of psi, it would look something like this. Both sides you have minus kx, and it can sometimes be written as e to the power minus k times mod of x, because here it's negative and here it's positive. Now the next step is to find these three values, to find the values of b, f and k, and once you've done that, then this will give you the solution. So for that, we'll use a property which we've seen earlier, which is that psi of x is always continuous and d psi by dx is continuous except where v is infinite. And the second rule we'll actually prove in a few moments, because we'll use that in this one, but we'll use the first one right now. We got psi of x is equal to b e to the power kx for x less than 0 and f e to the power minus kx for x, this is greater than 0, this is less than 0. Right. Now we know it has to be always continuous. That means it has to be continuous at x is equal to 0. But we know psi of 0 from the left side is b and from the right side is f. So they need to be equal. So this is the first thing we find out, that b is equal to f, and indeed both sides have b e to the power kx and b e to the power minus kx. So now we are left with finding the value of b and k. So here what we'll do is we'll actually integrate the Schrodinger equation and try to get the value of the change in d psi by dx. So the Schrodinger equation is minus h square by 2m d2 psi by dx squared minus plus v of psi is equal to e of psi, and we'll just integrate by multiplying these by dx. This will come outside, dx, 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 and we'll integrate it over a small interval minus epsilon to epsilon, where epsilon is a very small number. Now the RHS will turn out to be 0 because E will come outside and psi we know cannot be infinity. So the integral of psi over a very small interval has to be 0. So this has to be 0. Now V psi of dx in the normal case would be 0 except where V is infinity. If V is infinity, then even though this is a very small interval, the integral will not be 0. And what is the LHS? Well, that can easily be written as minus h square by 2m, and what is this? This is the difference between d psi by dx at these 2 points. So d psi by dx at E minus d psi by dx at minus E or minus epsilon, and this is equal to, let's take the minus to the other side, so this is equal to integral minus epsilon to epsilon v psi dx. Now in ordinary cases, if V is not infinite, then the RHS would be 0, which means d psi by dx at epsilon would be equal to d psi by dx at minus epsilon, which means we've proved this result that whenever V is not equal to infinity, whenever V is a finite value, d psi by dx has to be continuous. However, when V is infinite, we can actually find the value of this term LHS, and that will be equal to integral minus epsilon to epsilon alpha minus alpha delta x psi of x dx. And what will that come out to be? It is basically minus alpha psi of 0. So the LHS is equal to RHS, which gives us that delta of d psi by dx is equal to minus 2m alpha by h square psi of 0. But what is delta of del psi by dx? On the LHS, it is equal to, the derivative of this is bk e to the power kx, and on the right it is minus bk e to the power kx, and at x is equal to 0, these two terms become 1. So bk and minus bk. So this is basically equal to 2bk. But actually it's minus 2bk because we want it from this side minus this side, the right side minus the left side. And psi of 0 we know is equal to b from both these points, so that cancels, 2 and 2 cancels, and what we are left with is k is equal to m alpha by h square. So our goal was to find b, f and k. We found f, that was equal to b, and now we found the value of k, that is k is equal to m alpha by h square. So what is left is to find the value of b. So psi of x now is b e to the power kx for x less than 0 and b e to the power minus kx for x greater than 0, with k being equal to m alpha by h square. So now how do we find the value of b? Well, the last thing that is left to do, we still haven't normalized this wave function, so that's what we'll do right now. We'll normalize it. That means the integral from minus infinity to infinity mod psi square, which here is just psi squared because it's psi star and psi, so it's 2b squared e to the power minus 2kx dx. And now 2b, why do I have a 2 here? Because the integral from minus infinity to 0 will be the same as the integral from 0 to infinity. So we can just take the integral from 0 to infinity and multiply by 2. And this we know is equal to 1. But what is this equal to? When we integrate this, 2 will come down, and what we'll be left with is b squared by k, which tells us that b is equal to root k, which is equal to root of m alpha by h. Also, what is the energy? the energy is equal to minus h squared k squared by 2m, because this was the original definition of k, root of minus 2me by h squared, right? So this is the energy, which if we calculate it, put the value of k, comes out to be minus m alpha squared by 2h squared. So this is the final solution. Psi of x is equal to root m alpha by h e to the power m alpha by h square x for x is less than 0, and root m alpha by h e to the power minus m alpha by h square x for x greater than 0, with the energy being equal to minus m alpha squared by 2h squared. And as we expected, the energy is negative because we assume the energy to be less than 0. So this is the complete solution for the bound state. The graph would look something like this, which means the highest probability would be finding the particle near x is equal to 0, and there would be a 0 probability of finding it very far away from the origin. Now let's move on to the E greater than 0 states, which are the scattering states, because this is the first question we've done in which you get both bound states and scattering states. And this will come out to be somewhat similar to the free particle case. So the initial part of the solution will be pretty similar. Let's say x is less than 0. The equation we'll have is d2 psi by dx squared is equal to minus 2me by h squared psi. But what will happen in this case is we'll write it as minus k squared psi. And the reason for that is E is greater than 0. So this term is greater than 0. What we'll get is k is equal to root 2me by h square, which also tells us E is equal to h squared k squared by 2m. Right. So the solution once again, in this case, we'll not have a e to the power kx plus b to the power minus kx. In this case, we'll have a sin kx plus b cos kx, because this is minus k squared. But that can better be written as a e to the power iota kx plus b e to the power minus iota kx. So this is for x is less than 0. Similarly, it will be f e to the power iota kx plus g e to the power minus iota kx for x is greater than 0. And then we'll have the boundary conditions. The first is psi is continuous at x is equal to 0. This tells us a plus b is equal to f plus g, and the other is d psi by dx, delta of that, the same thing we did in the previous case, delta of that is equal to 2m alpha by h squared times psi of 0. But what is psi of 0? A plus b. And this is equal to delta d psi by dx, and d psi by dx in this side, which I'll write it as psi dash, will be iota k times a e to the power iota kx minus iota k times b e to the power minus iota kx. But what we'll do is at x is equal to 0, e to the power iota kx will simply become 0. So we have iota k times a minus b. Similarly here, psi dash will be iota k times f minus g. And so this is equal to iota k times f minus g minus a plus b. So this is the first equation we have, and this is the second equation. And you can manipulate them yourselves. I'll just write down the final result which it gives, and that will be, first is f plus g is equal to a plus b. The second is f minus g from the second equation about d psi by dx. This is equal to a times 1 plus 2 iota beta minus b times 1 minus 2 iota beta, where beta is equal to m alpha by h squared k. So these are our two equations. Now we have two equations, but we have four unknowns. We really only need to find the ratio of the size because we need to find the ratio of the probabilities. But let's look at what the problem is before this. Let's look in detail at the actual problem. This is the potential, 0 everywhere, then minus infinity, and then once again 0 everywhere. And then you have waves. On the left side, you have one wave, a e to the power iota kx. Then you have another wave, b e to the power minus iota kx. And here you have f e to the power iota kx and g e to the power minus iota kx. Right. And this wave is traveling towards the right. This wave is traveling towards the left. This is traveling towards the left. And this is traveling towards the right. So this is basically a scattering problem where you have a potential and you have four different waves in four different directions coming and being reflecting and transmitting and stuff like that. So what we'll assume is we'll take G is equal to 0. And the reason we'll take G is equal to 0 is because this would become 0 and then it would become a scattering problem where A would be the incident wave, B would be the reflected wave, and F would be the transmitted wave. So the problem is slightly changed now. We are sending a wave which has the wave function a e to the power iota kx. We are sending it from the left side x less than 0. It reaches this potential well and it gets both transmitted and reflected. A portion of it gets transmitted, a portion of it gets reflected. And so if you put G is equal to 0 in these, the final result you will get is this. B is equal to iota beta by 1 minus iota beta times A, and F is equal to 1 by 1 minus iota beta times A. But what we need to find out is the reflection and transmission coefficient. That means if we send a number of photons towards the right in this direction, then a portion of those photons would be transmitted and a portion of those photons would be reflected. So what we need to find out is the ratio of probabilities of finding the photons. And the ratio of probabilities, we know probability is given by mod psi squared. So the ratio will be given by the ratio of these coefficients. So what we'll get is the reflection coefficient will not be B by A, which is a common mistake students make. It will be mod B squared by mod A squared. And this will come out to be, this will be multiplied by minus iota beta by 1 plus iota beta, and this will be beta squared by 1 plus beta squared. Similarly, the transmission coefficient will not be F by A, it will be mod F squared by mod A squared. And I'll repeat once again, the reason this is a mod squared is because we need to find the ratio of finding the probability of a particle, and the probability is given by mod psi squared, not by psi. And this comes out to be 1 by 1 plus beta squared, where beta is equal to m alpha squared h by k. And so we also see a result which is quite satisfying, r plus t is equal to 1, which should be true. The ratio of the reflection and transmission coefficients should be 1 because every photon is either transmitted or reflected. And we can write r and t not in terms of beta but in terms of the energy once more, and what we'll get is r is equal to 1 by 1 plus 2h squared e by m alpha squared, and t is equal to 1 by 1 plus m alpha squared by 2h squared e. And we can see that as the energy increases, the transmission coefficient increases and the reflection coefficient decreases. And that is what should be expected. With the higher energy, you would have more transmission and less reflection. So this is the solution for the scattering states of the delta function potential. We have one last problem left in the next video to tackle before we move on to the mathematics of quantum mechanics, and that would be the finite square well. Thank you.